Okay, here we are. I think this is approaching the end of the first part of the further mechanics curriculum. And we're probably going to discuss here core concept 9, and maybe there'll be a 10 if I have more to speak about this topic. But we're going to talk about a rather hard to intuit, or at least it has been for me, concept. And I'll go through that slowly with you, and we'll start with what I'm trying to explain, right? So just work with me on this. So just using this piece here and calling it a beam, right? A typical engineering structure, a beam, um, right? A rigid object, so it's got a certain mass, and I'm going to use this term called the uniform beam. So just remember that uniform beam, right? It's got uniform. And what is a uniform beam? A uniform beam means its mass is equally or distributed across its volume in a equal manner. So it's the density across the entire volume is constant, and therefore it has a very well-defined center of mass, which is fairly geometric. So its center of mass, I call it COM because that term becomes important, is easy to predict. So if the length of this beam was L, you'd have the center of mass at L by 2, right? So that's the idea. And we're going to work with this object and extend some of the concepts today with this. So let me start off this way. If I kind of want to hold this object like right at its center, probably just it's going to stay fairly balanced. A little bit of swing here and there, but let's see if I can do it. Clearly not. My hand is too slippery. But yeah, it stays. So what happens is, and I'll use this idea to illustrate it. So if that is my beam, that is my uniform beam, and that's my center of mass, which it is the center here. And if the mass is m, we know there is a force that is felt as mg by my fingers supporting it right at the center. I have a reactive force. R is equal to the negative value is just to say that it is opposing, right? And it's all balanced. I could now, that was one case, I could also just hold it on these two ends and it's just staying there, right? So it's almost like saying, this is how I supported it in the first instant at that point. In the second instance, what I'm going to do is I'm going to support it here. And I'm denoting this as just points, right? So you get the idea. So this object continues to pull down with mg, and there's reactive forces here and here. And because they're fairly equal, they're both equal, and they're usually mg by 2, right? Because and the same here, mg by 2, right? And so understand that, right? So that central mass kind of help with this. Now take this. We'll play a little bit with this beam example. If I were to hold this beam or this beam in my hand like this, now it's fixed on one end. In the sense that this side is fixed, any kind of pressure that this thing feels, if I was trying to give it a straight forward, it's really the force exerted here is not a straight line force. If you think about it, if I let go of my hand, it just flips up, right? It's like a bending force. It wants to flip this over, right? And it effectively, if the force was hard enough, it would break somewhere here and flip out. So that's a bending force. I'm not going to speak much about the bending force today, but I'm going to talk about something else, a little different, right? So imagine a case where, let's say I Let me make this a little nicer, but with my t-shirt and all of it might be a little harder. But if this was the case, and I was holding it here, it's almost identical to what you see on the board behind me, right? It's kind of balanced, right? But this end is free. This is like it's free to swing here. There's no bending force, just that one upward force that's holding it, right? So effectively, if this side was held, the center of mass is pulling it down this way, and then I'm giving it that support here. So all good. If I just now turn this a little bit, what's happening? You'd like to think that all the forces are the same, but it's actually not. There's a little bit more of a force that my finger now experiences was, if it's here, it's even higher, right? Versus if I was exactly balanced. And why is that? And we'll try and understand this a little more closely by looking at the same beam this time. If this beam was held, that was the beam. And if I was just holding it up here and here, you'd think, hey, this is in equilibrium. There is a force acting down. Are these two still the same? Are they equal, or is there a difference to this? Right? Now, in this particular case, yes. It appears like it's just being held there at that point, but I just created a situation where I changed this and I drew what is called as a hinged. So there's a hinge, which is basically that, and it's free to rotate. Now all of a sudden, almost I have a whole lot more effort that goes in here to bring this up. If I bring it up to the same level, it would just stay there, it'd be perfect. But there is something more that's happening here because this object is not getting that same fixed force up here. So there's a greater component here. And let's try to analyze this a little bit. And I'm going to try to state here, if the mass is m, if we didn't have gravity, there was nothing at all, and I just kept this beam as is, it would just stay there, right? First law, or law of inertia, means it would not want to move. Now, if I wanted to push it up here, this object is going to resist. If I just had a regular mass on a flat surface, it's at rest. If I wanted to push it, there's a force. There's the inertia, which is that body's resistance to motion. Similarly, here, it has a resistance not just to motion, but now it's rotating about this axis. So that is my axis here. This white chalk facing you, the camera, is the axis. This rotational inertia, and I'm going to use this term, rotational inertia, right? Inertia is a resistance to motion. Rotational inertia is a resistance to rotational motion. It doesn't want to move along this direction. I would need to apply a force. But how do we understand how much this rotational inertia is? And effectively, the rotational inertia is simply its mass. So take the mass of this object, and assume this is the center of mass. If we take that linear distance and call that r, rotational inertia would be equal to m times r squared, also called the moment of inertia. And why moment of inertia? Because it's about a particular point. This reflected to the object itself, but this reflects the object's moment of inertia, meaning its rotation about a particular point. It's very different if I was going to say, that's the point now at which I'm going to hinge it, right? And I'm going to try and, it's very different. very little force needed. Its resistance to motion is much lower because I am now much closer to its center of mass. So in my mr square, my r is reducing because that's where I'm hinging it. So its resistance to motion is very less. And as soon as I get all the way to its center, right there, bang at the center, it's much, much lower, right? Or actually, if you get right there, there is no more r, and it doesn't have moment of inertia. Inertia just exists because it's in that same axis. There is no. If you notice here, we have this, and we have a perpendicular axis to it, and it was moving here. So it's two dimensions here, and the axis is a third dimension. But if I was here, there was no such thing. It was basically the center. There was no parallel distance between the center of mass axis and the rotational axis. They come together, right? And therefore you would get a zero value. You wouldn't get a negative value, of course, because r doesn't become negative. And if you move the r that side, it just is. If I gave it a negative directional r, the square just makes it positive, so you wouldn't get, and mass can never be negative. So just keep in mind that if you have problems where you try to calculate moment of inertia and if you're getting a negative value, something's not right. So that's just an idea. So understand that the body has a moment of inertia, which is its own tendency or its own capability to resist motion, right? So that was just something to know about a body and that term called moment of inertia. But I want to now extend that to another term, a term that I think becomes very useful because a lot of examination questions like to be very crafty and give you some problems to do. So I'm going to take that same body and now say, okay, let's forget the non-gravitational world. Let's take a real world and say, okay, now we have this body here. That's the beam, uniform beam. Trying to make my beam as uniform as I can, right? That's my uniform beam with its center of mass here, right? I'm going to define its length as L. So the center of mass, and then I'm going to hinge it here. So that's my hinge. So there's no reason to worry about any forces there because it's just a free rotation. What would happen under normal circumstances if I just let it be? Gravity would just let it swing down and it would come back down. But if I now want to apply a force here, this is the force I'm applying. What is that force going to be? And if you try to do it yourself, you'll actually notice that there's a point where you can feel that there's a slightly higher exertion that you're going to be doing. So how do we understand this? Right? I am applying a force here this way. So right away, there's a little bit of an angle coming up, if you notice. Right? That's my force F. What is the body doing? The body's got its own, and that, thanks to the nature of gravity, it's m times g because the mass of this is m. It's L, right? And I know that if this is 1/2 L, and so is this, right? Should come up with a nice way to do this. Okay. Now, how do I get an idea of this force, and how does it feel if I was doing it at this very end versus if I came closer, versus if I came even closer? How do you get a feel for it? And you might have seen this. This also becomes clear sometimes if you have a seesaw, right? And you have a seesaw. You've got something in between here, and then you've got somebody sitting on this end and somebody sitting on this end. That's a very common view. Sometimes you also see people using a lever to pick something. They put it in there, put in a force here, and you can lift a much heavier weight on the other side, right? The same principle applies. I've just shifted this hinge point to somewhere along here, and we can play with the math. But first, if this beam was staying in equilibrium, what exactly is going on? it's not as easy as saying F is equal to mg. It's not, because you can feel it intuitively when you move. There's something that's not, doesn't feel like the same thing. So here is where I'm going to define a concept called moment of force. Just like inertia's effect around a rotational axis is the moment of inertia, the effect of this force about an axis. So moment of a force, just as you have moment of inertia, is always about a particular point. So when you have a problem, you always pick a point at which, about this point, not at the point, but about this point. It's how all of the force is acting on this object. So if it was just sitting, just plain and simple, in my palm, right? You'd think that there's two forces, but in reality, there's a force here, and it's free to move. There isn't anything holding it, right? And if there was zero friction, if it was smooth, at some point, just slip. It'd be like that, right? It's just free. So same as the hinge. I mean, it's just the free force. How do you realize these forces about this point, not at this point? Because this force is not really acting at this point. It's acting here, right? And the moment of force, let's say, if I make this as A, and say it is that times the distance. So it is, but is it really just that distance? That's where you have to watch out. It is the perpendicular distance. So it is equal to F times the perpendicular distance, not this linear distance of the object, but instead, and I'll switch to another color here just to illustrate this. It is this distance. So now, if this angle was theta, and I know L, and you can do this either theta from the top, you can go from the vertical. Watch the angle. I'm interested in this distance. I know L, which means cosine theta is this side divided by L. So this side is equal to L times cosine theta, the perpendicular distance, L times cosine theta. For a body in equilibrium, whether it's this staying in its place, wherever that is. So as you can see, if I come really close to the center of mass, I need a lot more to hold it. And if I go past the center of mass, it's even more. I can feel it on my hand. It's almost like it's going to slip. Yeah, it's going to swing out, right? But for it to be in equilibrium, the following have to hold. The effect or the moment of this force and the moment of the force due to gravity have to be equal for this body to be in equilibrium. So when you have a beam or something like that in this condition, not a fixed beam, because there you would do something called bending torque, right? Here, moment of a force is also called, they use the word torque, but I'll get to it as a segue into the next part of further mechanics. But for equilibrium in this particular beam, so this is moment of the force about point A, force F, moment of force F about point A. And then I'll say at equilibrium, what happens? This moment of this force about this point and moment of this force about this point, they stay equal. I would be able to write F times L cosine theta would be equal to this force, which is mass times acceleration due to gravity, times, what is it now? If this is half of L, that's half of L. What is my perpendicular distance of interest is that. So if this area, this is also 1/2 of L, this is simply, now if I make this generic and said its center of mass is, let's say, R from the point of interest, then the moment will automatically adjust these values to that. So this L by 2 is just this linear distance. So this would be L by 2 cosine theta, and this lengthy area would be L cosine theta, right? Just so you get it. And at equilibrium, this happens. If you had multiple forces, you would do exactly the same. You would choose a direction, put all forces in that direction here, and everything in the opposite direction here, right? And this can have, you can have multiple forces. You can be presented with interesting problems come in here. They can combine this with, let me say I take out my standard issue beam, uniform beam. They're all uniform beams. If I take them out just for illustration, show you a simple problem, and if I said, hey, that's my hinge on which I have a beam, and at this end I have an elastic string, and I can't tell you, I just know its natural length is L, but now it's L plus X, and then I give you a mass, and then if you know the modulus of elasticity, you can calculate the moment, equate the moment to get this force, use that as the tension on the elastic string, do your Hooke's law calculation, and solve this problem. And you can apply this in many cases. You can apply it in a case where you just have a beam that's resting on a surface with or without friction. If you have friction, then of course there is that component of friction that's acting here as well that you can think of if you're taking the moment about another point. Frictional force, don't forget that. But otherwise, it just sits here, and let's say I have this force here, and then I hang a key punch on the very end there, and then I'm holding it up this way, or I'm supporting it additionally here because I have a load coming up here. What load prevents this from flipping over, for example? So you can have problems like that, but they're all effectively solved by taking the moment of the different forces about a single point that is your point of interest, and then you take the moment of forces, you build the equilibrium equation. Hopefully this gives you a view, and that sort of, I think it set us up for a good segue into going into circular motion, where we'll talk more about rotation, what happens there, and torque, and all those concepts. But I think just for that first part of further mechanics, this idea should be quite helpful, right? So remember the term, uniform beam. Classic question: when you say uniform beam, basically center of mass is at its center. That's a given. If it's a non-uniform beam, then its mass distribution is different, so its center of mass is shifted away. And then when you do moment of inertia, this term R becomes known as the radius of gyration. Gyration. People have, yeah, whatever is the right way, right? But I don't believe that topic is addressed, at least in the first part of further mechanics. In the later part, they do have a little bit, but not in too much detail. It's really an engineering concept, so I don't see that very much in most high school curricula. But we'll talk about it when we get to rotation and things like that. We'll get into it a little bit, right? And then remember, this moment of a force about a point A is basically that force times the perpendicular distance between that force and the axis of the point, right? That's something to remember. You will have cases where you might get a force along, if I put something in such a way that the force was in a different direction. Supposing this was a flat surface and I had a little sphere here, and then the sphere would have a normal, the angle would be along the radius of the sphere. So you might have to resolve it or figure out how the geometry works for that, but different ideas. But this is fundamentally what you need to remember, and the equilibrium. I think I'll leave it at this. I think this should be good enough for most problems that you will see until this stage, even with friction and even with collisions in single dimensions. I think fundamentally this is good enough, but it sets the tone for us to now say, hey, if there's a hinge or point and there are forces about rotation, and that's how we will enter into the second part of further mechanics, which begins with circular motion. I'll see you in that video.